Hello, everybody, and welcome back to overview and a helicopter view of calculus. For those, this video. I'm recording it, and I'm going very slowly, and I'm doing a lot of repetition because it's intended for somebody who has no clue, or somebody who has no clue of what does this. Let me switch back here. No, we want to go here. Yes, of this dy over dx is this notation, and we talked about it. And again, for those of you who have studied with me, I don't like memorization, and I don't like you to memorize anything. And unless, you might need to memorize a few formulas at the end when it gets difficult, even though I will derive it for you, we will explain it. You might still think it's very difficult, and I would rather, memorize it. I had a student, she was great. We did calculus. We did the overview, the rules of differentiation. She didn't even have any, issues with the chain rule and the implicit differentiation. At the end of her differential calculus, there is something called hyperbolic functions, and it was like of that form. It's the sine, it's a sine of h of x. And this has to do with the natural Euler number. It's e to the power x minus e to the power minus. There's a minus x here divided by 2. And of course, we explained it. I explained it to her, and we spent a lot of time. And she understood how we came up to the differentiation of this specific sine of h x hyperbolic functions. But at the end, she told me I would rather, just memorize the formulas of this specific dy over dx. And that's understandable. But for you now, at this early stage, to tell me that, you still have a problem and you need to memorize what we talked about, all we talked about, that is the idea of we're studying this quantity y with relation to x, and we at a particular point on a graph. So this quantity y could be a distance with relation to time. It could be giving us making a velocity vector with direction. It could be product cost and price. What we talked about, what will be the cost of producing the next iPad or the next TV or the next item. It could be anything we can think about. I'm going to give more examples. And the idea is for you to think of it geometrically as the limit of the secant of a particular point that is approaching that point of conversion right here. Let's call this point of conversion, we called it A in many instances, as B, another point from right or from left, approaches A, the secant, the limit of the secant as B approaches A, or as the delta x, the coordinate of B, are almost on top of the coordinate of A, which means delta x approaches 0, but it's not 0, it's approaching 0, and the secant becomes a tangent at that point. So the slope of the tangent is the differential. Very simple. You have to link it to the chord, to the secant, and you have to think of it as 2 points, one point approaching the other, being almost on top of the other one. And that means their x coordinate, their delta x, or if we're talking about time, it's delta t, and we're going to do a delta t very, very soon. Their delta t approaches 0. As the limit from the right, when delta x or delta t approaches 0 from the left, limit of that secant, equals the limit as delta x approaches 0 from the right. If it's equal, that means it's differentiable. If it's not equal, that means it's not differentiable. It could be continuous, but not differentiable. And we gave the famous example of the y equal absolute value of x. And we said that this one is continuous at 0, 0. But when delta x approaches 0 from the left, we have negative values, and we plugged in that delta x in our f of x, which we can do, and we got an expression with delta x that looked like this. And we said since it's approaching from the left and it's negative values, we got a -1, and when it approaches from the right, this becomes a positive value and it equals +1. Thus, therefore, the new function that we have of that f dash of x or f prime of x, or of the gradient of the slope, looks like this. This is your +1. This is your -1. It's not differentiable here, but it's differentiable for the rest of the graph. It's not differentiable here, but it's differentiable for the rest of the graph. Look at the original graph. It's not differentiable here. It's edgy. The tangent, there is a crossing here. The secant does not approach gradually. For the differential to happen, the secant has to approach gradually. So all of that good stuff, you don't really have to memorize it. If you need to memorize stuff like that, then we need to dig deeper into other points and try to help you with other building blocks. So maybe you forgot what's a chord, what's a secant, what's a tangent. So we need to work on that. But so far, there is nothing for you to memorize, even if you have no clue what differential calculus is, and you're totally new to this. Now, the next function, the exception function that I'm going to give, is called the floor and the ceiling function. And for those of you who are familiar with JavaScript and with Python, you do the floor. This is the floor right here. And this is, sorry, it looks like this. There is a hole here. This is wrong. It's this one. And this is the ceiling. And it looks something like this. So there is a hole. Let's see here. See this hole on 2? And then it's fulfilled right here. And then there is a hole on 3, and it's fulfilled with the 3 on top here. And there is a hole on 4. And I believe I have another example on the board. And it goes like this. See, where the integers are happening, again, this function, for those of you who never heard of it, it's called the floor or the ceiling function. And it has to do with integers and with the values between the integers, of course. We're going to talk about that. So integers, 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. You see there's a hole here on 1 and on +1, and again, it's fulfilled here. Then there is a hole here and it's fulfilled here. And so you see there is a jump. It's called a discontinuity, a jump discontinuity. So you tell me, well, when there is an integer, there is a jump discontinuity. So it's not continuous. I studied limit, and that means it's not continuous at that point. That means what? It's not differentiable. Yeah, I agree, but that's not my point. My point is for you to prove that with the delta x concept, with this tiny slicer, with this tiny addition, delta t or delta x. And we're going to do it, and it's very easy. But first, in the books, in many books, it's called floor and ceiling. In other books, it's called the largest integer functions. And I actually tend to agree on this one, because it, brings it closer to your mind. And I like to give some example. Again, you don't have to memorize anything here. If you see this floor function, that means this. That means they're giving you a value, let's say like 1.3, and they tell you y equal 1.3. Okay? So what do? This is a floor function, and the definition of a floor function is the largest integer not greater, there is a not, the integer not greater than x itself. So if you come and you put it simply on a number line, where does 1.3 goes? 1.3 goes right here, right? What is the largest integers here that is not greater than x? Is it 2 or 1? It's 1, because if you put 2, it will be greater than x. That's all there is to it. So you have to go by this definition that has not in it. All you need to remember to conceptualize it and to understand it is you need to understand that in the definition of a floor function, I am looking for a value that is the largest integer not greater than x itself. Okay? Let's give another example. If you have a 1.8, y equal floor function of 1.8. Okay? What is the answer going to be? Where do you put that 1.8? You put it right here. And you have the same concept. Do I choose 1 or 2? Again, it's not greater than x. So if you choose 2, you'll be greater than x. So it's 1. Very simple. Okay? Now, the ceiling is almost an opposite concept. The ceiling has to do with the smallest integer, not less than x. So the smallest integer, not the largest, the smallest integer, not less than x. So if I have something like that, the same one, 1.3, y equal 1.3. Where is 1.3? Right here, but not less than x. Do I choose 1 or 2 in this situation? I choose 2. That's it. Okay? Again, if I have something like 1.8, I choose 2. The smallest integer, not less than x. Now, let's go to negative values. They're, again, not difficult. If I have a floor ceiling of minus 1.5, where does the minus 1.5 go? Right in here. Floor minus 1.5. What is the definition? Using not. Integer and not. It has to do with integers and it has to do with not. The largest integer not greater than x. Would that be minus 1 or minus 2? It has to do with minus 2 this time because minus 1 is greater than minus 1.5. So the answer is your minus 2. Okay? Because if you choose minus 1, the integer will be greater than minus 1.5. Minus 1 is larger than minus 1.5. Again, this is math of 4th grade, 5th grade. Again, it builds off each other. You need to remember these simple things, and we will talk about them. Like, remember in the last video, we talked about a simple equivalent fraction, a over b equals c over d. Same here. You need these things, you need to remember them, and I'll remind you of them as we go. Now, how about the ceiling function of minus 1.5? The ceiling function of minus 1.5 equals minus 1. Because you're choosing the smallest, this one. You have the ceiling, you're going to go choose the smallest. Think about it this way. In the floor, you have the floor, you're choosing the largest. So you're choosing the smallest integer, because this has to do with the integer. It's an integer function and the values between the integer. The smallest integers not less than x, which is in this situation minus 1. Because if you choose minus 2 is less than minus 1.5. Okay? You need to remember these things. I would, if I were you and if you forgot them, just spend 5 minutes on a scratch paper and just remind yourself of these, what happens in the negative value on a number line. Okay? So speaking of that, now we understand what a floor function or a ceiling function is, and we understand that it has to do with integers. And when x is an integer, here, x equal the floor function of x equal the ceiling function of x. What does that mean? Let's give it with a minus example. If x is minus 4, what is the ceiling or the floor function of minus 4? Again, let's go with the definition. What is the floor function of minus 4? We have the floor, we're looking for the largest on top, the largest integer not greater than minus 4, which is minus 4, equals minus 4, okay? Equals minus 4. Now, if I have it like this, as a ceiling, minus 4 here, I have the ceiling. I have to look now for the ground. So I have to look for the smallest integers not less than -4, which in this situation is again -4. Okay? Because if you choose -5, -5 is less than -4. As simple as that. Okay? Now, having said that, let's switch back here. Let's switch back here. And let's go back to A. Okay. And let's not forget, I have, the same way I reminded you of that simple, -2. What did we do? -2 is less than -1.5. This has to be, for you something that you should never, ever forget in your life. Something very simple. And the equivalent fraction. I have to remind you of your numbers. Just the sets of numbers. First, in the middle, what do we have? N counting numbers, which are what? 0. They have 0. 0, natural counting number. This is this N. We write it like this with 2 bars here. 0, 1, 2, 3, 4, 5, 6. Then you have the Z, right? This is what we're talking about, the integers. They include -3, -2, -1, and the 0. And 1, 2, 3, 4, 5, 6, 7. And then the following circle or set is what? Is your Q before the R, with again almost two double layer here. Something like, what is Q, rational number? Something like 5 divided by 3, something like 0.125, something like -7. Yeah, because -7 is -7 divided by 1. Okay, something like 1.5. Okay, and then we have the real number, R, double layer, double vertical bars. R have what? R real numbers, they have the -2, -1, they have the 0, they have the 1. They have something like the radicals, square root of 2, which never ends. The Euler number, E, that never ends. You have the pi, which is 3.14, 15, 92, and then it never ends. It keeps going and going and going. It's not finite. And then the last layer and the last set is what? Is your complex number. For those of you who started taking complex number, they have -1, they have 0, of course. They have 1, they have the I, and they have 1 plus I, they have 2 plus 3I. We'll talk about that in complex number. Okay, so Z, we're just talking Z here with this function. Just a reminder, those are the little notes that you have to have in the back of your mind in order to build off. Math builds off small information that you have gathered throughout elementary school and middle school and grade 9 and 10 and 11, all the way to you taking this college exam and going to the first year of college. Okay, now speaking of that, if we are to find, let's say, the floor ceiling of pi. What's pi? 3.1415. So floor, what's the definition of floor? Definition of floor, floor function, no, sorry, not floor ceiling. Floor function is, we have the floor, we have to look for the largest integer not greater than 3.141592, which in this situation is 3 and not 4, because if you choose 4, you'll be greater. Now, if you do it in the opposite way and you want to find the ceiling function of pi, you will have to choose 4, because the definition tells you you have the ceiling, you have to look for the smallest integer not less than x itself. X itself is 3.141592. So if you choose 3, you go less than x, you have to choose 4. So the idea is very simple for you. And again, you're going to come and tell me, what does this have to do with derivatives? I can see the jump discontinuity. I think it's not differentiable when x is an integer. Totally agree. But I want to do it with the delta x. To prove to you that even a difficult function that you might not be familiar with, we can solve it with the delta x. Now, Speaking of that, we want to approach as delta x approaches, let's say, 0 from the left, and delta x approaches 0 from the right. So let's go ahead and do it. When x is in integers, not like a pi, not in between, when x is element of z, what happens? The floor functions become x plus delta x. You just add it, as simple as that. And the differential definition that has to do with geometry is what? Is the limit of that secant of f of x plus the delta x that you added minus f of x divided by delta x, the whole thing, as delta x approaches 0 from the right, has to equal the limit of f of x plus delta x minus f of x as delta x approaches 0 from the left. So it's basically the following. It's limit, let's start with delta x from the left, of x plus delta x, right? Minus what? Minus x, minus f of x, the whole thing over delta x. Now, when you're approaching from left, that means negative zone. That means it's the integer of 1 less the x. So if you're approaching again from the left, it's the negative zone. So that means it's the integer of 1 less the x. So here, what do I get? I get x minus 1. I go to x minus 1. X minus 1. And what's the floor function of x? It's x. Remember, when x is an integer, we said x equals floor function of x equals ceiling function of x. When x is an integer, not a value between the integers like the pi. So in this situation, I get x minus 1 minus x divided by what? By delta x. So let's move to a new page. What do I have now? I have x limit. Teacher always wants you to put that limit. Limit as delta x approaches 0 of what? X minus 1 minus x divided by delta x, which equals to minus 1 over what? Delta x. Delta x is in the negative value. We're approaching from the left. So this is a very small negative value, right? And this is minus 1. When you take minus 1 and you divide it by a very, 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 very tiny small negative value, what do you got? What do you get? You got plus infinity. Again, if you're not, you need to conceptualize it. This is what we're doing here. If you have a minus 1, try it on your calculator, and you have a very, 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 very tiny number that your scientific calculator can't even fathom or understand. Try a very tiny number, 10 to the power, I don't know, minus 27, and put minus 1 on in the numerator, and try to do the division. What do you get? A very huge number. So the tinier this delta x becomes and the negative value we're approaching from the left, the higher and the bigger the equation, the whole equation becomes, and it goes to plus infinity. So the limit as delta x go to 0 from the left is plus infinity. Now, let's study it from the right. Okay? Limit as delta x approaches 0 from the right of x plus delta x, floor function minus x over delta x. What do I get here? I get just x. It's not x minus 1 because it's approaching from the right of a floor function. So I get an x. And remember, what is the floor function of x when x is an integer? It's x itself. So I get this over delta x. So I get 0 over delta x, and I get 0. Over there, I got plus infinity. And here, as the limit of delta x approaches 0 from the right, I got a 0. So basically the limit from the left of the secant approaching a tangent, that's, even if you didn't understand, you're not very sure about this floor and integer function, all you need to remember, the limit as the secant of the approaching a tangent from the left is not equal the limit from the right. So it cannot really approach a tangent at that point. And that's why you have that jump, that discontinuity jump, that, where is the board? That is behind me on the board, that you see it right here, okay? You have the discontinuity jump. And that's how it's not continuous, and that's how when it's an when the x is an integer element of z, okay? So when x is element of z, it's not continuous and it's not differentiable. So dy over dx, when x is an element of z, is dne. You see that in some textbook, does not exist. Okay, so now what happens when x is not an integer of the same, we're talking about the same one, the floor function. We're not talking about the ceiling. We're just going to deal with the floor. I don't want to confuse anybody. I'm just telling you that even when you see a function that you're not familiar with, you use the same concept. If it's very difficult, if it's something that you're not used to see, you're not going to get that in a test. You just get that, with your teacher, so they can explain things to you. So when x is not an integer, like a pi, if let's say x equal pi equal 3.14, 15, 92, whatever, all the way down, the d over dx, that means the differential of this floor function of x, we're talking about the floor, equals the limit as delta x goes of that secant as delta x goes to 0 of what? X plus delta x, again, minus floor of x over delta x. And we just did up there that x plus delta x is what? Is x. And we said, look at it, 3.14, okay? 3.1415. We did this one before. What is the floor of 3.1415? It's basically 3. You have to choose the definition says when you have a floor function, you have to look for the ceiling, and you have to choose the largest integer that is not greater than x itself. If you choose 4, you are wrong, because 4 is greater than x itself. So you choose 3, you choose x again. So I have an x minus x, and the whole thing is divided by delta x, and I have 0 again. But again, if your teacher is to give you a function like that, since you're not a mathematician and you're not studying math, you're just taking calculus, they will only stick to the integer part. And they will tell you find out using the calculus principle, which is delta x approaching 0 from right, from negative in the negative zone, from right from the positive zone, and from left is not equal to delta x approaching 0 from the left in the negative zone. And that's how it's not differentiable. And that's how I can prove to you, sir, teacher, that there is this jump and this jump or discontinuity in this floor function. Okay? Very simple idea. Again, we can use this delta x or delta t with any function. I'm going to go ahead and use it now back. I'm going to go back to physics and velocity and use it with a very, very simple physics problem. But before that, let me emphasize one more thing. Again, we are studying differentiability like when we talked about the y equal absolute value of x at a particular point on the graph. Now, for example, if you have that rectangular hyperbola, it is continuous here, differentiable here, but y equal 1 of x at x equals 0 is not even defined, right? Remember that? It's not even defined. So no continuity and no derivatives at x equals 0. But at other points, at other location, it is defined, and it is differentiable, and it is continuous, okay? So again, that's why you gotta be very careful. We're studying a specific point, a specific location, or an interval. So another example would be, for those of you who are taking sinusoidal function, which means y equals sine of x and y equal cosine of x, you know that you have your interval between -1 and +1. Now, if you have something like y equals sine of 1 over x, okay? You're still between -1 and +1, but the period has changed. So the function is going to move up and down faster. So we can't really find a value for it because it's a value for it to head towards, because it doesn't convert to a value. It doesn't really converge to a value. Look at it. Instead of going like this, sinusoidal, it's going to go like this. Before it goes, you know, in a wave with a wavelength and a wave shape. It's between -1 and +1. It's gonna go like this, because you put it 1 over x. You change that period, so there you can't really find a value for it to head or to converge towards. Okay. So we will study this one in particular later on, the sine of 1 over x. It's very important. But just to give you an idea that we are studying a certain location, a certain point, a certain interval. Like we gave the easy example of rectangular hyperbola, y equal 1 over x. At x equals 0, it's not even defined. So there is no differentiability. It's not continuous. There is an asymptote, all that good stuff. But the sine of y equals sine of 1 over x, we will discuss it more as we go. Now, what I'm going to talk about, I'm going to give an example of how you can add that delta x or delta t even to a second. Simply because, you know, it's tinier than a second. It's tinier than a nanosecond. It's a concept. That's why you can go ahead and add it anywhere. So let's say there is a car driving on an inclined curve, and it has the shape and the function. Let's make it easy. What do I have here? F of x equal distance equal 2t squared. It's going at a speed of 2 meters per second. Okay, per 1 second. Which is what? The distance over the time. So after 1 second, the car is at what? After 1 second, the car is at a d equal f of x. Very simple. 2, right? I'm sorry, 2 times 1 after 1 second squared, right? Equals 2 meters. Okay, so far so good. You know, you tell me, okay, I totally agree. So far so good. Let's say the car kept driving and at this constant speed until it sped for 8 seconds, zigzag. Like I always tell you, you know, you zigzag for a nanosecond or for a few seconds. Let's say, make it easy, you zigzag for 8 seconds and to pass a slow moving car, but unfortunately this car ended up in a collision, in a crash. I'm not making it dramatic, it happens all the time. The police pulled the trip recorder. It shows that, you know, to show them how fast the car was going, very simply, and how hard it hit the brakes. They also checked the skid marks, the damage. But unfortunately, since the car was old, let's pretend the car was old, they couldn't, the speed recorder, the trip recorder didn't tell much and wasn't very telling. So the only 2 meters per second that they got, the constant original speed, wasn't really enough. Since there was a casualty, let's say, they brought in a team of forensic science, and they also checked the tire marks and the skid marks and all that good stuff. But they still wanted to figure out a speed at an exact instant in time when the crash really happened. of course, they have their own computer-based algorithm and they have all that good stuff. But let's try to help them. Let's try to figure out what do they base that computer algorithm on, okay? How do they come up with that idea of this computer algorithm? And I'm making it very simple. We said as at t equal 1 second, the distance we said equal 2t squared equal 2 meters, right? We agree. So let's invent a time, this delta t. Yes, we're going to invent it. It's an invention. It's an addition that we can do. A time so short that it doesn't matter. We're going to call it delta t, and it can help us find and track and predict the speed at any point in time. Once plugged into an algorithmic code. So once we plug in this delta t into an algorithmic code, we can find out the speed at any time. So we had speed at 1 second. Now at 1 plus delta t, what it might happen? What is the derivative? I have a derivative because the secant as 1 plus delta t, I want to find out the secant as 1 delta t as it gradually approaches the graph and becomes a tangent, right? So I want to find out the limit as delta t approaches 0 of f of what? 1 plus delta t minus f1 at 1 second divided by 1 plus delta t minus 1. Okay, so far so good. I'm studying at 1. So I took a specific point, 1 time equal 1 second. And I'm studying 1 plus delta t. What happened after that 1 plus delta t? That's all I'm doing. Okay? Now, the original function is y equal what? D equal f of x equal 2t squared. So the limit as delta t goes to 0 of 1 plus delta t squared minus f of 1, I'm studying at 1, divided by 1 plus delta t minus 1 equals what? Let's expand, equals 2, and then this equal 1 plus delta t squared plus 2 delta t, and I close, minus 2, because 2 times 1 is 2, divided by delta t. Okay, let me go to the board. Maybe this way you can see it better. Okay, let me go to the board here. Let's erase that. And I'm doing this whole thing just to show you that you can add this delta t to any point on the graph. So if you start from a point t time equal 1 second, okay, what is the graph itself? The graph itself is f of x equal 2t squared. So you're studying the limit of that secant as delta t here, not delta x, approaches 0. And this secant gradually approaches this point, and it becomes a tangent at this point. So f of x plus delta x, or f of t plus delta t, minus f of t divided by what? T plus delta t minus t, which makes it delta t. Now, t plus delta t is what? Is this. 2t squared. But I want 1 plus the delta t. I want to add from that specific point. So it's 1 plus delta t squared minus the f of 1. I'm studying, remember, we have to study at a particular location, at a particular point. I'm studying at t equal 1 second. So it's 2, you open your parentheses, instead of t squared is 1 plus delta t squared minus the f of 1, the whole thing is over delta t. Okay? Now, you expand, what do you get? 2, okay? 1 plus delta t squared plus 2 delta t, and minus what? Minus what? Minus 2, because the whole thing f of 1 is 2, okay? If you put 1 here, what do you get? F of 1. You get 1 squared, that's 2, so minus 2, divided by delta t. What do I get now? I get 2 plus 2 delta t squared plus 4 delta t minus 2, the whole thing divided by delta t. So far, everything is very easy. I'm just doing it at 1, and I'm adding this delta t right after 1. I can do that. It's very infinitesimal. It's very tiny. It's just a concept. The same way infinity is just a concept and not a number. This is a concept, okay? So what do I do now? I can do 2 minus 2, right? And I can take 2 delta t, and what am I left with? Delta t. Remember, I want to get an expression in the form of delta x or delta t. So I took a factor 2 delta t, and then what am I left with? Delta t plus 2, right? The whole thing divided by what? Delta t. Now, what do you have left? 2 delta t plus 4, okay? 2 delta t plus 4. That's your final answer. But what is delta t? It's 0. Okay? So as delta t shrinks towards 0, the speed becomes what? 4 meters per second. 4 meters per second. Okay? As delta t shrinks towards 0, after this 1 second, if the accident happens right after this 1 second, the speed becomes 4 meters per second. And that's, let me see back here. Let's go back here. Let's go here. Okay. And that's how you can add this delta x or delta t to any point on the graph, even to the simplest and the smallest value, which is 1 second. You can find out exactly what happened after that 1 second. Okay? Now, I'm going to go back to another example. You're going to tell me, oh, car, and 1 second and 2 seconds, cars, they speed at, 65 miles per hour and 100 miles per hour. Give me something, more in line with real life application. Okay, the final problem that we're going to do is actually, you might see something similar to it in your books. I got it from a French book. And this was given as a real life application of something that actually they said here, it's a real life story that really happened. So I don't know if that's true. We'll deal with it. There's a basketball training, and a basketball is thrown upward during practice with a velocity of 80. I did translate it from metric system, 80 feet per second. Okay. And its height after t second is given by function or equation q terms of t equals 90t minus 18t squared. So the original equation f of x is qt equal 90t minus t squared, t being the time, of course, and the height is in feet, because I did translate this from the metric system. Okay, so the ball actually hit an older lady as it's coming down, and the lady fainted and passed. They didn't say passed out or passed away. I hopefully only passed out. Now, what is the maximum height reached by the ball? That's the first question. So eventually the ball is going to fall down, right? And so the maximum occurs when the ball turns around. So there must be a horizontal tangent at that height or at that point, okay? This is something that you can imagine yourself. Anything like a soccer ball kicked, a basketball kicked, a projectile, a rocket launched. If it goes, eventually it's gonna come down, okay? And if this is the ground, we're gonna study the elevation later, but we're gonna pretend that this is where the player threw the ball, and let's pretend that this is where the lady is. This is what they want you to. So it hit a lady on the head. So eventually the ball is going to, fall down. And the maximum occurs where? Here, right here. Where the secant gradually approaches a tangent at that point. And it does. It's not like your y equal absolute value of x. It's not edgy here. It's not pointy. It gradually approaches a tangent. So far, so good. So this maximum point right here, where the tangent line is horizontal, this is the maximum point where the derivative then, the dy over dx, okay, is, or dt here, because we're studying in terms of time. We don't have an x, we have a t instead. So your dt, your derivative, okay, equal at this particular point is going to equal 0. So q prime of t is going to equal 0 at that point here. Okay, let's move to a blank page. And let's first of all find our f dash of x, or here it's q dash of t. And we're doing this with respect to time here. Again, the idea of relativity. So the original, I believe, was, let me see, what was the original? 90t minus 18t squared. So the derivative of 90t is just 90. We will study that soon. Minus the derivative of 18t squared is 36t. Yep, 36t. And it's going to equal to 0 right here, because the tangent is horizontal. The slope is 0 here. The slope is what here? 0. The tangent is horizontal and the slope is 0. So this q prime of t at this particular point, at the max, right where the ball is going to fall, is going to equal to what? To 0. So we made a new function now. This is the gradient function. And this is the slope function. It's q prime of t here. Okay, we're studying it in terms of t. And it's linear in this case, and we can find the distance from that new function, and we can take it, plug it back in the original, and find the distance. And that's what we're going to do. So what we can do here is 90 minus 36t equals 0. That means 36t equals what? 90. And t equal 90 divided by 36, which is 2.5 seconds. So now I have my time. I can take my time and I can plug it back in the original. The original again was what? I believe the original was 90t minus 18t squared. Okay, so if you put 90 times 2.5 minus 18, 2.5 squared, you get, this is 225 minus, let me see this, yeah, this is 112.5, so I get 112.5 feet. Their difference is also 112. Okay, so because of this curve and the tangent, we were able to come up at this particular point where the tangent is horizontal and the slope and the gradient is 0. We put the new function equal to 0. Your dy over dx is 0, and that's how we came up with this idea of new function q prime of t equals 0 at that particular point. Now, the problem goes further and asks you what is the velocity of the ball at 72 feet. Now let's draw this again. And actually, let's do it on the board. Yeah. Let me go to the board and I'll come back here because I like to do this one on the board. Here. Okay. Let's go to the board. Old-fashioned, old school. I like everything on my board. Just bear with me. As long as you're getting the idea and you're not memorizing anything. That's what I worry about. Okay, so there is a ball here. Okay. And then it's going in that shape. Right here, we found out that the maximum height is what? 112.5 feet. From the metric, we put it in feet. Okay. And then this is where the lady's head was. You know, she was sitting in the, in the stands, and this is where the basketball were thrown from. we're not talking about the ground and elevation. We're just making it easy like this from here. Okay. Now the question is, what is the velocity of the ball at 72 feet? So 72 feet could be here, right? Could also be here, right? As it's coming down. And again, that's why it's velocity, because as it's going up, the vector is going to be going this way, this direction, and as it's coming down, it has to go in the downward direction. So with 72 feet, all you need to do, you just need to do the original equation, 72, here. What was the original equation? I keep forgetting. I apologize. What's the original equation here? My original equation is... Oh, okay, yeah. 90t minus 18t squared. I apologize. Keep forgetting that original equation. Okay, so it's 90t y equal 90t minus 18t squared. Okay? So all I need to do is just say this 90t minus 18t squared equals what? 72. That's how you link anything to the y vector, y-axis, or the y variable. So 72 equal 90t minus 18t squared. Okay, so far so good. If I bring it like this, it becomes 90t minus 18t squared minus 72 equals 0. Do you agree? Very simple, very easy. I see 72, I see 18, I see 90, and I believe 18 is a factor. So I can take minus 18 and I can open my parentheses, right? And I can put t squared, right? Minus 5t. Do you agree? Because I'm getting minus 5t, look. Minus 5t. So that's minus 18 times minus 5, you get plus 90, minus 5t, plus 4, to get minus 72, equals what? Equal your 0. Now, two numbers, we will talk a lot about factoring, and completing the square, and all the methods that you should know. We will talk about them in calculus and as an extra key starter and refresher. But, here you have an easy thing, minus 5 and 4. So, minus 1 times minus 4 equals plus 4, and minus 1 plus minus 4 equals minus 5. It's very simple, it's very easy. So I have t minus 1, right, times t minus 4 equals 0. So you have t equal 1 and t equal 4. T equal 1 second, of course, and t equal 4 seconds. So now you take those and you plug them where? You plug them in your velocity, because they're asking what is the velocity of the ball at 72 feet. So let's go back here. Okay, now you plug this into the velocity in the q prime t, the new function that you came up with, and you can say that q prime of 1 second, we have two, t equal 1 and t equal 4, equal 90 minus 36t. It's 1, so that's 54 plus 54 feet per second. And then if I go ahead and I do q prime of t, or q prime of 4 seconds, that's 90 minus 36 times 4, 4 times 3. So that's minus 54 feet per second. Okay? So far so good. And that's very, very understandable. This trajectory, actually, it makes a lot of sense, because at 72 feet, you know that you're doing everything correct. This is your velocity here, and this is your velocity here. Upward, downward, this is your maximum height, where the horizontal tangent and the slope equal to 0, and you put q prime of t equals 0. Okay? Now, with that being said, let's switch back here before we wrap it up and get ready for the final video. What else do I need to talk about here? Yes. Now you might think of, you're giving me a lot of projectiles, and velocities. How do we link that to what you are going to start teaching me when you start teaching me their differentiation rules and derivatives? Yeah, look at that point where it says maximum height equal 112.5 feet. This is the point that is called a stationary point, because for a tiny instant in time, the ball is not moving up there. That's why in math, we call it a stationary point. And it's also a turning point here, because it's changing what? Sign and direction. So let's move back here. And let's move back here. Right up here. This is a stationary point, because for like a tiny instant in time, the ball is not moving. Tiny instant, like less than a nanofraction of a second. The ball is not moving. And it's also a turning point. Remember that very well. A TP, I call it, so you can remember it. A TP, turning point. That means, what does a turning point means in math and in calculus? A turning point means it's changing sign and direction. So it's changing sign and direction. And again, this is not for you to memorize, but we need to exercise and give more examples of this, so you will just come to your mind just like that. Sign and direction. Turning point means you're changing sign and direction. Okay? Now let's talk more about it for another minute before we wrap it up. So remember that famous exception that I always like. It's this one. Y equal absolute value of x. Okay? At x equals 0, it's continuous. It's a turning point because the slope here, the gradient, it changes from a negative at x right here, from a negative value to a positive value, right? So it is a turning point. It is a turning point here, y equal absolute value of x. We have a turning point. The slope is changing from a negative to a positive value, right? And in other functions where the slope changes from positive to negative, it's also a turning point. But here with this exception, at x, at the origin 0, 0, this is not a stationary point. Because for it to be a stationary point, the derivative dy over dx, the differential must equal 0, and it's not differentiable here. You see what I mean? How we linked all that stuff together now. So that was a physics problem, or in some of your books, they put it in the math book. They're related anyway. All science is related. However, stationary doesn't mean, turning point doesn't mean stationary. Meaning, we gave the exception. This is a turning point. That means the sign and the direction. Turning point, TP, means a change in sign and direction. The sign and the direction of the slope is changing, of the gradient, of the rise over run is changing. However, it's not stationary in math, meaning the derivative at that point, it's not differentiable. We cannot make dy over dx equal 0 here, okay? But in our example that we gave on the board, yes, we can make this dy over dx equals 0 right here, and we put it as q prime of t equals 0. And with this, I conclude. In the last video, we'll relate differentials with an overview to economics and accounting, and profit and loss and quantity and prices and supply and demand. I'll see you in the next video.